Should I start? Okay. So, yeah. So, So last time, so we saw that if you let gamma as a discrete subgroup of PSL2R, then this gamma acts nicely. It acts properly discontinuously. On the hyperbolic plane. And as a consequence, we have, it has this action has a fundamental domain. For this action. And we saw a method of building such a fundamental domain, so mainly the Dirichlet domain, okay, which in principle is an infinite process, so it's sort of it's an intersection of all these half spaces that we get, but which turns out to be typically some kind of finite a geodesic polygon. If your gamma is finitely generated, it's some kind of geodesic polygon with finitely many sides. So that's what a Dirichlet domain looks like. So remember, so these half spaces are points. So the Dirichlet domain is with respect to a certain sort of base point, and you look at where, let's say, the generators of gamma go, and each of these would have a perpendicular bisector. So these geodesic segments, which are geodesics, and these cut out a polygon. Okay, so that's what the Dirichlet polygon is, the Dirichlet domain. Okay, and that turns out to be a fundamental domain for the action. And this polygon, it kind of translates of this tiles the hyperbolic plane. Okay, the tiles H2. Okay, so copies of this are kind of taken by this action of gamma to things which have disjoint interiors, and they kind of fill up the whole of the hyperbolic plane. Okay, so that's what tiling means. All right, and let me just mention. So the Dirichlet domain is so as I said a geodesic polygon. So it's a polygon with geodesic sides, and it has sides which are paired with, okay, so if you look at the definition closely, you'll see that, so if you have a side, excuse me, so if you have a side S of your Dirichlet domain, then you also have some other side S prime, which is paired with it. Okay, so there'll be some element gamma that takes S prime to S. Okay, so that's some additional information you get that this Dirichlet domain comes with. Okay, so it's not just a geodesic polygon. If you remember this action of gamma, you'll see that sides of the geodesic polygon are paired. Okay, so for every side there's a corresponding side, and there's a transformation in gamma taking one to the other. Okay, so that's what I call a side pairing, and yes, yeah. So it'll necessarily be finitely many at around a vertex. It's a locally finite tiling. That's a consequence of the fact that this action of gamma is properly discontinuous. Okay, so you can't have sort of infinitely many tiles around a vertex, and so a little bit of argument tells you that would violate proper discontinuity of the action. Okay, so yes. Okay, I'll write a bit larger. Okay, so a fact which I won't prove is that, in fact, this gamma the Fuchsian group is generated by all these side pairings, by the side pairings. Okay, so And we'll kind of we'll see examples of this in a second. So once you have the Dirichlet polygon, you'll have a bunch of elements of gamma that pair different sides. The group gamma is generated by all these elements. Okay, so that's a sort of a fact which I won't prove now. So let's look at an example. So we've already seen, well, we've told you some examples of this. So you've seen these elementary subgroups, right? So there were iterates of a hyperbolic element or iterates of a parabolic element. Those give you, so those are discrete groups. These are Fuchsian groups. And we have also told you about PSL2Z, okay? So I don't know whether you've worked out why the fundamental domain I showed is indeed a fundamental domain, but you can, okay? Nice exercise. Maybe I'll come back to it during the tutorials. But let's look at another, yes, yeah. Even number of sides, yeah, maybe, so you shouldn't take my drawing very literally, so yeah. I do have even number, but this is not quite what I want to maybe, yeah, okay, so. Right, so, yeah, so now let me look at another example, which I'll sort of revisit in this lecture again and again. So this is going to be, so I'm going to start with a polygon, okay, and then build the Fuchsian group out of it, okay. So instead of this way, so it's going to be my fundamental domain. I want to be like this. So it's going to be, it's going to be this polygon. This is an ideal polygon. All the vertices are at infinity, okay, and I want this to have, let's see, so maybe 0, 1, and 2, okay. Yeah, so let's just see this example for now. So let me look at two transformations. So two elements of PSL2R. One of them is this, okay, and the other is this, right? Can someone tell me whether these elements are hyperbolic or parabolic or elliptic? Sorry? Yeah, so how do you check? Yeah, so the trace. Yeah, so this is trace is 3, this is trace is also 3, right? So see, these are both hyperbolic elements, and if you check how they act, so there's an A of, so let's see, so A should take this geodesic to that, okay? So if you look at A of infinity is what? It's 2, right? And A of 0 is 1. Okay, so and yeah, so and you can convince yourself that this vertical geodesic from 0 to infinity goes to this geodesic from 1 to 2. Okay, and what about B? So B is going to be the other one, right? This here. So what happens to B of 0? So B of 0 is yeah. Yeah, so what do I want? Yeah, so maybe this is not quite the correct one. So what do I want? So I want B to pair this to this. So, and someone suggest an element which does that? So let's see. So where do I want? Yeah, so B of 1, Z plus 1 by Z. Okay, so let's see. So B of 0 goes to infinity, and B of 1 goes to 2. Okay, so that seems to work. Okay, so let's, yeah. No, but this is, yeah, this is not a hyperbolic element anymore, right? So no, this is not quite what I want. By the way, so this, yeah, so, oh, sorry? No, but it's still not hyperbolic, right? Sorry, let's see. So Z. No, that's not determinant 1. Yeah. So, any other suggestions? I want an element that goes from here, Z plus 2. Okay, so now what happens? So 0 doesn't go to infinity, right? So, yeah, so this doesn't quite work, right? So what do you want? Yeah, so this is not quite what I want, right? So, unfortunately, yeah, so what works? So let's see, so yeah, so you want, so this geodesic to go to this geodesic, right? So you want, so B of 0 to go to infinity, and B of 1 so 3Z by Z. Okay, yeah, this seems to do the job, right? And this is a hyperbolic element. Sorry? No, this is okay, right? It's 3, 0, determinant 1, right? It's okay. Yeah. Okay. Yeah, so this works. Okay, fine. All right, so we have these two elements, okay, that takes this geodesic to this and this to that. So I claim that the group generated by A and B is a Fuchsian group. So to see this, what you have to check is it acts properly discontinuously, right? So what do these two elements do? So if you look at A, so I want to say that this polygon that I've drawn here, let's call it F, is indeed the fundamental domain for this action, okay? So where does A take F? Well, A takes this geodesic to this, but it takes everything on the right of this geodesic to the right of this, right? So this will take F to a domain which looks like this. So this is A of F, okay? So it pushes this F to something which has interior disjoint from the interior of this, okay? So, and similarly, you can check that B does the same. So B will take this F to something disjoint. So you need to check that, so A of interior of F intersected with interior of F is empty, and similarly B takes its disjoint to itself. And in fact, what happens is all iterates, all words that you can form, for example, in A and B, are all going to push this F disjoint from itself, okay? And it's going to push it further and further, the longer the word is. So you can, in fact, if you draw it in the disk model, what does this look like? So this ideal quadrilateral would look something like this. And let's say the side pairings are this A and B. So then this generates a tiling. As you build, let's say you act on the picture by some word in A and B. So you can make it a long word, right? And you hit F with that, you get to another tile. And there's a tiling of the fundamental of H2 by these fundamental regions, which looks something like this, right? So there's a tiling by these ideal quadrilaterals, okay? And every time you hit F with some word, it takes F to one of these tiles, right? And you can draw, so these tiles are arranged very nicely in this case. It looks like a tree, right? So you can, so there's a 4-valent tree, right? So maybe you've seen some of these in your topology mini course, right? So, and every time you go in the vertical direction, it's like acting by B, okay? And then sort of in the, and the other way around, it's B inverse, and every time you go in the horizontal direction, it's A, right? So if you give me a word, W, right? So it takes you to a specified sort of vertex in the tree, right? And so there's a tile corresponding to that. Okay, so this tree gives you an address to each of these tiles, and every word takes you to a unique tile. Okay, so let me just summarize. So as a consequence, maybe what you have is first of all that this group generated by A and B is a free group. Okay, so why? Because so no word W, which looks like this, is trivial. Okay, so if something is not a free group, then there'll be a relation. Okay, so then it would have acted trivially on this picture. It wouldn't have moved F at all, right? But here you see that no matter what word you take, you go to a different tile. Okay, so this can't have relations. So it's a free group. And the second thing that you see is that's what we really want. So gamma acts properly discontinuously. Okay, so I won't go more into that, but you can check that if you take a compact set, it will intersect only finitely many of these tiles. Okay, so if you are acting by gamma and you take a sequence, then so remember you're going off in the tree somewhere, right? So if you take sort of a sequence of elements in gamma, you'll be looking at a path in the tree. So there are only finitely many of these vertices that lie in a compact set, because finitely many tiles that lie in a compact set. So you'll go out of the compact set if you look at sufficiently many elements. Okay, so this tells you that orbits can't sort of accumulate. You can't all lie in a compact set. Okay, so this tells you that gamma acts properly discontinuously. Okay, so is this kind of picture clear of this action? So on. All right, so another thing that I want to mention about this particular example, so there's an observation. So it's kind of a note that, so in this example, gamma acts freely on H2. So remember, what's a free action? Free action means that there's no sort of a fixed point, right? So there's no element. So if there's some element in gamma such that fixes a point, so then that element must be just the identity element. Okay, so every element moves points. Okay, so there's no it doesn't have an element that fixes a point. And you know what these elements are? These are elliptic elements, right? So this is another way of seeing this is so in other words, so gamma has no elliptic elements. That is, the gamma is, so if you want to use algebraic terminology, so it's taut and free. There's no finite order elements, right? So if a Fuchsian group has elliptic elements, that elliptic element better be finite order, right? So here there are no elliptic elements at all. So it is no elements of finite order. Okay, so so this is an interesting, it's an important thing. So if this happens, so if in general, so the remark is that if gamma is a torsion-free Fuchsian group, then gamma acts freely and properly discontinuously on H2. Okay. So once again, so if it acts freely because there are no elliptic elements, right? So there's no element that fixes a point. So when gamma acts on the picture on H2, then you really move. So every element of gamma moves points. Okay, moves all points. Okay, so if this happens, then if you have such a nice action, so then the quotient of H2 by gamma is a surface. Okay, so this is happens if you act by a torsion-free group. So because you've seen surfaces before. Surface is something which is locally homeomorphic to R2, right? So this map becomes a covering map, right? So it is every point in the surface has infinitely many these pre-images which are permuted, right? So the orbit. Okay, so this is a consequence. So this is how you would get surfaces if you start with something which is torsion-free and Fuchsian. Okay. Now, for example, in this case, what happens? What surface do you get if you take the quotient? Well, yeah. So it's something like something's funny going on here, right? You take a square, identifying opposite sides. So that's familiar to you, except this vertex of the square is at infinity, right? So it's not really in the space. So what you get as a quotient is, so H2 mod this gamma is going to be it's going to be a punctured torus. Okay, so I'm drawing the puncture like this because if you look at what happens to a neighborhood of these ideal vertices, so these kind of tapering ends, they kind of these gluings fit together, these four of them, and then form a neighborhood like this. And so as you go out, the distance between these geodesics going to 0, right? And that accounts for this little tapering end here. Okay, so it's kind of getting narrower and narrower here. Okay, so a once punctured torus has a hyperbolic metric. Okay, so you might have learned that a flat torus doesn't have a hyperbolic metric, right? So, but if you puncture it, okay, and allow a complete metric where the puncture sort of goes off to infinity like this, then there is indeed a metric, and this is this is an example that gives you such a metric. Okay, so. All right, so in general, we want to get surfaces like this, let's say of higher genus. So let me just mention a general theorem that allows you to build Fuchsian groups just like we did here. Okay, so here we started with this polygon that we wanted as a fundamental domain, and then sort of came up with some transformations which did some side pairings. Okay. And then concluded that it's Fuchsian. And we kind of saw it by seeing that it acts properly discontinuously. So the more general theorem is called the Poincare polygon theorem. And it says the following. So let D be a geodesic polygon with side pairings. Okay, maybe just like here. and you have some conditions. So let me just, so such that, so A, so any interior vertex, let's see, so I'll just introduce this term in a bit. So any vertex cycle corresponding to an interior vertex in H2 gives either the identity element or an elliptic element of finite order. So that's case A. Let me write it down and then I'll say what a vertex cycle is. And B, so any vertex cycle corresponding to an ideal vertex is a parabolic element. So gives a parabolic element. So these conditions need to be satisfied. So then the group gamma generated by all the side pairings of this polygon you started with is a Fuchsian group. And it has fundamental domain D with fundamental domain D. Okay, so what's a vertex cycle? So a vertex cycle is a chain of vertices. It's a chain of vertices identified by side pairings. So let me just not go into details. So I'll just mention an example. So it's some kind of, so this polygon has different vertices, right? So they're paired. So the side pairings identify vertices. You know, each time you can have a side pairing, this vertex gets identified to that, and then you take another side pairing and that it gets identified. So you have some kind of chain of these side pairings, gamma 1, gamma 2, and so on, and a chain of vertices, and eventually you want to end in V. Okay, so that's what a vertex cycle is. And when I say gives a parabolic element or gives identity element, I want I mean this composition. So gives the element, there's an element gamma 1, gamma 2, gamma n. So that's some element of the group gamma, right? So it's a composition of these side pairings. Okay, so that's this element. So you want, so whenever you have a polygon, you want these vertex cycles to be, so if you start with a polygon which has a vertex in the interior, okay, so maybe you have all ideal vertices, like in this case, but if you had something in the interior, right, so let's say this V, you can follow these side pairings for these sides, which is V is incident, V belongs to, and then you look at this, follow these side pairings, and maybe you come back to V, okay, and this collection, or this product of these elements needs to be either the identity element or an elliptic of finite order. Okay, so that's the condition A here. And if it's an ideal vertex, so let's see what happens here. So what's the vertex cycle in this case? So the vertex cycle, so suppose I pick a point, so pick one of these ideal vertices, so V here. Okay, so V under A will go here, right? So V under A goes to, let's say, V1, which is this. And then under B, it goes here, V2. Okay? And then, So then if you go A inverse, right, takes you to V3. So we're almost there. So B inverse takes you back to V. Okay, so B inverse takes you back to V. So what element of the group does this vertex cycle give you? It gives you, well, B inverse, A inverse, or maybe, how did I write it? Okay, I wrote it. It doesn't quite matter, but here it is. Okay, so it gives you this element. All right, so that's the vertex cycle corresponding to this ideal vertex. And this needs to be parabolic. So the thing to check, if you start with the polygon and do these side pairings, and you want to get a Fuchsian group, you want this to be parabolic. And this you can check. So if we had these expressions of A and B written down, right? So you can check that forms a parabolic. This element is a parabolic element, okay, by some calculation. And that tells you, the Poincare polygon theorem would have told you that this generates a Fuchsian group, okay? So in fact what happens is gamma is generated by all the side pairings. That's fine, but there are also relations. So you can write down a presentation of gamma, which are all the vertex cycles appearing in A. Okay, so in fact, the Fuchsian group that you get has this presentation. So you can actually tell what the Fuchsian group is. Okay, so that's what happens. Okay, so in this case, yeah, so it's just a free group and two generators. Okay, so they have this case A doesn't arise. Okay, so all right, so we are almost there. Remember what we want are these, this genus 2 surfaces, genus 3 surfaces, and so on. So as a consequence, now we can we can form Fuchsian groups whose quotients are any surface of genus 2 and higher, right? So as a consequence, you can get a genus 2 surface. So what polygon do you start with? Well, you have to start with an octagon. Okay, so it's got 8 sides, and you want to start with. So D is a regular octagon with all interior angles equal to pi by 4. Okay, so you want to start with this. It's a hyperbolic octagon, remember. So such a thing doesn't exist in Euclidean. So in Euclidean geometry, a polygon being regular means all the sides have the same length, right? So a regular polygon means that all the interior angles are determined, right? So they have no choice. So for example, if you look at an equilateral triangle, right? So all sides the same. That means that these must be 60 degrees, right? So what about a regular octagon? So can you tell me what the interior angle for a regular octagon in the Euclidean plane is? So what are these angles? Right. So what is a multiple of pi? It's 3 pi by 4. Right? So each of these angles must be 3 pi by 4. Okay, so if it's Euclidean. So you can't dictate what the interior angles are, but here you can. Okay, so we've already seen for a triangle, right? You have an ideal triangle, right? Which is all interior angles are 0. So that's like an extreme case of a regular, like an equilateral triangle in the hyperbolic plane. But how do you get? So why does this exist? So why does such a D exist? Well, the answer is well, it's a continuity argument. So let me just sort of say what it is. If you look at, so this regular octagon, regular hyperbolic octagon has a side length associated with it, right? So the length of the side, which is all the same. So if L is very small, okay, so if L is small, then what you have in the hyperbolic plane, let's say in the Poincare disk model, you can think of this regular hyperbolic octagon as sitting inside, or in a little neighborhood of 0. But you know that up to first order, the metric here is very close to Euclidean, right? And so the angles, which are basically it's the first order information, right? This is the difference between derivatives, sort of this finite difference. So this is these angles would be very close to being to the angles of a Euclidean polygon, Euclidean octagon. Okay, so here, so if L is small, the interior angles of a hyperbolic octagon with side lengths all L is close to 3 pi by 4. Okay? And if L is large, so then you're kind of approaching this ideal octagon case, right? So, and for an ideal polygon, these distances, these angles are 0, right? So this we've seen before. So if L is large, then the angles, the interior angles, are close to 0. So somewhere in between, there's some value of L, okay, for which this angle, interior angles, are exactly pi by 4. That's why such a thing exists. Okay? Is that argument clear? Yeah, so that's why this D exists. And then you can sort of pair sides. You not only do you need a regular octagon, a geodesic polygon, but you need to specify side pairing. So I'm going to pair sides like this. So there's going to be some A1 that takes this to that, a B1 that takes this to that, right? And then an A2. So you might have seen this before, right? So and you have A and B2, which takes this. So this gives you a side pairing, okay, for this polygon. And now you need to check that this vertex cycle condition. So there are no ideal vertices. So the only thing is this A. So if you pick a vertex, then and you follow these side pairings, you'll get a vertex cycle. And because of this condition, because all the interior angles are pi by 4, every time you pair, you're essentially it's a hyperbolic translation, but you're rotating by an angle which is pi by 4. So it turns out that this vertex cycle would involve 8 pairings, okay, and you come back to itself. And every time you're kind of rotating by pi by 4, and so by the time you come back, you get the identity element. This composition is identity. So let me just mention, so this angle condition ensures that the vertex cycle, can anyone guess what the vertex cycle is? I mean, what element it gives? Element, so it's some kind of composition of elements of these side pairings, right? Some kind of composition of A1, B1, A2, and B2. Right. So it gives you this product of these commutators. This you might have seen before, right? So in the morning, right? So it gives you this vertex cycle. And this vertex cycle, because of this condition, is the identity element. Okay, so then you indeed get a Fuchsian group. And what Fuchsian group do you get? Well, you know that topologically, if you take such a polygon with 8 sides and you identify sides in this pair, in this fashion, you get a genus 2 surface. Okay? So this gives you, so the quotient, so this implies that gamma generated by A1, B1, and A2, B2 is a Fuchsian group. It will have this one relation, which I'm not writing down, which is this, right? So it's a fundamental group of a genus 2 surface, okay? And its quotient by gamma is a genus 2 surface. And you might have seen how to see this, right? So you kind of, so conversely, if you cut along certain curves on a genus 2 surface, a hyperbolic surface, you cut it and you open it out, you'll get a polygon which looks like this, all right? Okay, so, yeah. Yeah, that's right, yes. So you're forming a surface by this quotient. So this must be the universal cover. So H2 is a simply connected space, right? So, and what's the surface S? And pi 1 of S, the fundamental group must be gamma, right? So that's a sort of a consequence of this, okay? So, all right, okay, yeah, thanks. So, okay, so and similarly you can get, yeah, so in general, so any genus G greater than or equal to 2 surface acquires has hyperbolic metric arising from a similar construction, right? From a similar construction. So, so what polygon do you then choose, by the way? So let's say you want to get a genus G surface. What is one possibility? You start with a? Okay, so what 4G do you take? Do you take a regular, should be the interior angle there then? Yeah? Right, they should all add up to 2 pi, so it better be something like 2 pi divided by 4G, right? Which is pi by 4G. So in general, if you look at 4G gone with pi by 2G, right? So angles, all interior angles. Such a thing again exists because of this continuity argument. Okay, so then you do some side pairings, and the side pairings should satisfy that relation you've learned, right? The product of commutators is one. So then you get some Fuchsian group whose quotient is a genus G surface. And you can write these down explicitly if you want. You can sort of give coordinates to these vertices, and just like we did before for the ideal quadrilateral, right? You can write down transformations that pair sides. Okay, so all right. So you can get lots and lots of these. And you can vary these polygons, by the way. So you need not have taken a regular octagon. You could have taken an octagon which is not regular, okay? But it should still have the fact that the side pairings and the vertex cycles are identity. Okay, so then it would again give you yeah. That's right. Yeah, that's the only thing. Yes, that's you have. So as long as you have a polygon whose interior angles add up to 2 pi, an octagon, and you have that the sides are paired, so they better have same length if 2 sides are paired. Then if you construct a group generated by all the side pairings, it will give you a genus 2 surface. Okay, so this is what is known as the space of all these. So if you fix a genus, and you look at all the Fuchsian groups, okay, which give you a genus G surface, then that's called Teichmuller space or moduli space. So so this is what was meant to be, subject of the last lecture. I'll sort of say a little bit. So the space of all Fuchsian groups. So this is the next topic. So there's a space of all Fuchsian groups, gamma. such that H2 mod gamma is a surface homeomorphic to to SG. So as SG is the genus G surface, okay, where G is bigger than or equal to 2. Okay, so now, I mean, this kind of construction tells you that such gamma exists, right? So, and I just kind of told you that there might be more than one such gamma, right? There's an entire space of such things. And this space of such things, I mean, so this is what, so this space, it's called Teichmuller space, TG, or moduli space, and MG. And these are kind of important mathematical objects which connects with different fields of mathematics. And these two differ by something called marking. So I'll sort of indicate now. So these are marked surfaces, and these are, if you look at, are marked Fuchsian groups, and these are unmarked. Okay, so without any markings. Okay, so let me just say without markings. Okay, and let me say something to to kind of motivate why we need, sort of two different, these two different things. Why do we need this notion of a marking? Okay, but this is what we are going to try to explore a bit now. Okay, so to try to see how we define the space of all these Fuchsian groups that give you the same surface. Okay, so topologically the quotient surface should be a genus G surface. Okay, but the groups are changing, so they give you different hyperbolic surfaces. Okay, so this is what happens. So let me sort of now go towards what these spaces are. So as a warm-up, I want to talk about the moduli space of ideal polygons. Okay, so this will be like the warm-up to understanding why we need these markings and so on. So let's, instead of talking about closed surfaces, let's just look at what the Teichmuller space, moduli space of ideal polygons would be. So space of ideal hyperbolic polygons. So what are they? So this width, let's say n number of sides. Okay, so now we don't have any genus, but we have sides of vertices, it's the same thing. Okay, so for example, so let me just sort of give it a name. So let's say Pn, okay, is the space of all ideal n-gons. Okay, so ideal n-gons. And I'm going to label, so this is going to be the analog of Teichmuller space. I'm going to, which has this marking. So with labeled vertices. Okay, so what are these? So as a set, so how do you define an ideal polygon? So remember that ideal polygon vertices at the boundary at infinity. Okay, so so here's my here's what an ideal polygon looks like. Okay, so maybe there's vertices x1, x2, x3. So this is an ideal hexagon, right? So you can label. So what labeled vertices mean that you're kind of numbering these. Okay, so if you permute them, then it's a different labeling. Okay, so you have a sort of an ordered tuple. Okay, so it's an ordered n tuple x1, x2 to xn of points in R union infinity. Okay, that's what this an ideal polygon with n vertices is. Okay, so is this clear? Okay, so this is what specifies an ideal polygon. If you know what n points are in an ordered way, okay, so then then you can say that, okay, this defines an ideal polygon with vertex 1 being x1, vertex 2 being x2, and so on. Okay, so that's going to be my sort of the analog of this warm-up example of a Titanless space. Now, what is P3, for instance? So if you look at, so that's the simplest case, right? So I mean, so you can talk of a polygon unless it has at least 3 sides. So what's the guess of what P3 is? Anyone? So what's P3? It's an ideal triangle, right? So what's the space of ideal? So okay. So I should say what how you sort of quotient. Yeah. So I forgot an important. How do you identify points? When do you say 2 points are the same, right? So so it's up to an equivalence, right? Otherwise, they're infinitely. I mean, there are uncountably many. You just choose some n points on the circle, right? In some order. So where P1 and P2 in the space are equivalent. Okay, so P1 and P2 are related if and only if there exists an isometry taking one to the other. Okay, so I'm going to want the isometry to be an orientation preserving isometry of the hyperbolic plane. So there's going to be an element A in PSL2R. Okay, that's an automorphism of H2, or an isometry of the hyperbolic metric, such that A takes P1 to P2. Okay, and the vertices go to the corresponding vertices. Remember, they're labeled. Okay, so such that and sort of the in an order preserving and the labeling of vertices are preserved. Okay, that is what I mean. Yeah, so there's this. There's 2 polygons are the same if there's an element, this hyperbolic transformation, this element of PSL2R, right? Hyperbolic isometry, which takes one to the other. Okay, taking these vertex labeled 1 in one to the vertex labeled 1 in the other, 2 to 2, and so on. Okay, so what's P3 then? What's the space of all ideal triangles to this equivalence? Sorry? Yeah, there's only 1 point here, okay? So there's a singleton. Why? Because there's one of the properties of, yeah, so one of the properties of Mobius transformations of things, the upper half plane, is that it acts triply transitively on the boundary, right? So you can take any 3 points to 0, 1, infinity. Okay? So up to this identification, there's only 1 point in P3. Okay? So there's only 1 ideal triangle with labeled vertices. Okay? What about P4? So if you look at an ideal quadrilateral, okay, so then, how many degrees of freedom do you have? Right? Yeah. So the guess is that it's R, and that's correct. And what happens? So, well, you can take 3 points you can fix to be, let's say, infinity, 0, and 1, and the other to be lambda. Okay, so so you might have learned this is the cross ratio of 4 points. Okay, if 4 points lie in the circle, then this cross ratio determines the quadrilateral up to this kind of isometry. Okay, so and this cross ratio, this value, so this R is actually, I mean, so you can think of it as so this is really all the lambda which is greater than 1. Okay, so that's what you can always transform your, so let's see, so you can always put your first 3 points into infinity, 0, and 1, and the other would be something from 1 to infinity. Okay, so So that as a set, it's homeomorphic to R. Okay, so this is just just a ray, like an open ray. Okay, so as a set, it's homeomorphic to R. Now what's now? Right. So now, so the moduli space is going to be things with unlabeled vertices. Okay, so just remember this now. So the moduli space, I'll call it MPN, is all the ideal n-gons, hyperbolic n-gons, okay, up to the same equivalence. Here, I'm not talking about any labels of these. So you remember here, you knew which was the first one, which was the second one. So here the equivalence is that, so if you look at P1, P2, so P1 is related to P2 if and only if there is some isometry, something in PSL2R, such that A of P1 equals P2. Okay, so you don't require anything about labeling being preserved, so on. So that's the moduli space. Now, what's the moduli space of these quadrilaterals? So remember, so the way we got this lambda was we sent x1 to infinity, right? And x2 we sent to 0, x3 to 1, okay? If things are not labeled, right? So if there's no ordering, it's just 4 points, then there's a choice of which you send to infinity, which you send to 0, and which you send to 1, okay? And suppose you chose a different set, so all of them. So suppose you chose a different permutation to go to infinity, 0, and 1. You would have gotten a different cross ratio, okay? And if you think about what happens here, so then let me just tell you the answer. So if you, so let me just say, so this. This lambda, this cross ratio lambda, depends on which 3 points you choose to be x1, x2, and x3. So suppose you had started with an ideal quadrilateral, okay, so which was x1, x2, x3, x4, okay? So you could have started numbering here, okay? You could have started numbering x1, x2, x3, x4, okay? Or you could have started numbering here. So so I want to preserve the order though, right? So so you could have numbered any of these, starting at any vertex. So this is an ambiguity of a Z mod 4Z action, right? So there's a cyclic group that you need to quotient by. So it turns out, so let me just tell you that, so the other choices of where you start gives cross ratio. So in this case, it's not that interesting. You get another, just one more possible cross ratio, which is lambda by lambda minus 1. Okay, so it turns out. So if you kind of, instead of choosing this, you chose a different one. Okay, you would have gotten a different cross ratio, which is lambda by lambda minus 1. So the moduli space of these ideal quadrilaterals, so this moduli space is going to be like this R, which is lambda greater than 1. So let's lambda greater than 1. This set quotiented with lambda, so quotiented with some equivalence relation tilde, where you identify lambda and lambda upon lambda minus 1. Okay, so these two give you are actually sort of different labelings. Okay, and this you can check that this is just lambda bigger than equal to 2, a fundamental domain for this. This is like an action of Z mod 2Z on this set. The fundamental domain is all points greater than equal to 2. Okay, so that's the moduli space of ideal quadrilaterals. Okay, so and let me just so tell you what happens for an ideal pentagons, and then leave it there. So if you look at P5, so then if you look at labelings, you can take, so these are ideal pentagons. So you can take 3 points to infinity, 0, 1, and then you have x and y, right? And so this as a set is sort of described by these pairs of points, okay? So x and y, so that so 1 is less than x less than y, okay? So as I said, this is homeomorphic to R2. Okay, it's an open domain, okay? But now if you look at the moduli space, so then this is actually P5 quotiented with a cyclic action of Z5, because the labelings can differ by choosing your starting point, choosing x1 to be different, and then sort of labeling the others according to this order in which they appear on the circle. So this identifies, so let me just tell you what pairs. So this identifies xy, this pair, with y minus 1 upon x minus 1 times xy, okay, and x upon x minus 1. So this pair goes to this pair under this action, and this defines an action of Z5 on this domain. Okay, so what does this domain look like? So if you try to plot it on R2, so let's say x and y coordinates. So then this would, x equals 1 is something like this, and let's say this is x equals y. So this Teichmuller space of ideal pentagons is like this domain over here, okay? And now, but moduli space is this quotient, okay, by this action of the cyclic group of order 5. And if you look at what this action does, if this action, this is just obtained by calculating what happens to the cross ratios x and to these vertices x and y, which are given by cross ratios. If you take a different combination to infinity, so a different vertex to infinity, okay, and the following vertices to 0, 1, and xy. Okay, so this is an easy calculation that gives you this. This has a fixed point. Okay, there will be a fixed point here, which is 0.1 square root of 5 by 2 square root of 5 plus 1 by square root of 5 minus 1. So there's a fixed point which corresponds to what? It's the regular ideal pentagon, okay, so which is sort of symmetric. All the vertices are at fifth roots of unity. Okay, there's some kind of ideal picture there where this cross ratio, these numbers x and y don't change no matter how you label it. Okay, so that will be a fixed point of this action, and otherwise this action will have a fundamental domain, which is I don't know what it looks like actually. So you can figure it out. There'll be some fundamental domain which will be the moduli space for these ideal pentagons. Okay. Yeah, so one can play around with what I mean. So more generally, I mean, these transformations are, you can check that if you do this 5 times, you get back to x comma y. Okay, and so it's a kind of, this is indeed an action of the cyclic group Z mod 5Z. Okay, so you see that this, yeah, sorry, yeah, right. Right, so if I don't care about labeling, right, so let's say in this case, okay, so in this case, if you don't care about labeling, suppose I want to label this as infinity. Okay, so then you look at the transformation, so consider the transformation that takes infinity to 0, 0 to 1, and 1 to x. Okay, so there exists a unique transformation which does that. Okay, so there exists an A in PSL2R that takes this. So now you're kind of secretly what you're doing is you're starting your labeling here. Infinity, 0, and 1. Okay, so yeah, so then you check where does y go? Okay, so, sorry, so let me do it the other way. So suppose, yeah, yeah, so suppose I want to kind of start my labeling here. So I want to send y to infinity, then infinity to 0, and 0 to 1. Okay, so I'm going to start instead of labeling from here, I'm starting here. So this is the new labeling. Okay, so what was y is now the new infinity. Sorry, now I'm. Do we have? Oh, I see. This wasn't an ideal pentagon to begin with. Okay. Sorry about that. So this is 1 here. So y goes to infinity, infinity goes to 0, 0 goes to 1. Okay? So then where does 1 go? So if you take this, then where does 1 go? 1 goes to the new x, let's call it x prime. And your x goes to the new y prime. Okay? And this, if you calculate, I mean, so you'll get this. You should get this pair. Okay, so yeah, identifying it because different labelings should give you the same, should be same points in the moduli space. Okay, so the labeling shouldn't matter. Okay, so you got one pair x, y if you labeled it one way, and you got another pair x prime, y prime if you labeled it in another order and starting from another. Those should be the same point in the moduli space. Not the Teichmuller space. The Teichmuller space are all sort of ordered, labeled points. So there you don't have any choice of which to send to 0, which to send to 1. Okay, so that's the difference between moduli space and Teichmuller space. Okay, so Teichmuller space will all be labeled things, and moduli space would be unlabeled. So so now that we know, sort of, this was warm up, but so now that we know what is this marking. So here, you don't have ideal vertices, but you have curves which generate the fundamental group. So this marking would mean that you label those curves. You label generators of the fundamental group. And moduli space would be things where you don't label the generators of fundamental. So let me kind of now come to one example of an actual Teichmuller space and moduli space. This is the simplest example, namely that of a once-punctured torus, which we've already seen. But now we've seen one example. We'll see all examples of punctured tori. Okay, so this is now the task. So Teichmuller space of S11, which is just once a torus with 1 point removed, with 1 puncture. Okay? What happens to bicycles once, from time to time. Okay. So how do you define a Fuchsian group that gives you so let me remind, so let me first define what this space is. You want to get Fuchsian groups whose quotient gives you a once punctured torus, right? So I'm going to write it in a funny way, but this is going to be written like this because it's going to generalize to all surfaces. I'm going to look for representations of homomorphisms, group homomorphisms, on the fundamental group of a once punctured torus. By the way, a once punctured torus is a fundamental group which you all know. So what's a fundamental group of a once punctured torus? Yeah, so it's a free group on 2 generators, right? So you can draw 2 loops, let's say A and B, which generate the, so pi 1 of a once punctured torus is Z star Z. It's a free group generated by A comma B. We saw it earlier, right? So when we constructed a Fuchsian group, we saw that Fuchsian group was generated by 2 transformations that generated a free group. Okay, that was actually the fundamental group of the quotient. Okay, so this is what this group is. So we want homomorphisms from this to PSL2R. Okay, so secretly, so let me say the curves are A and B, which generate the fundamental group. Okay, these A and B I want to kind of take to matrices, actual transformations. Okay, capital A and capital B, such that this is an isomorphism. So rho is is injective. So let me just say is an isomorphism to its image. And the image group, so image of this group is some gamma, right? Is Fuchsian, is a discrete group, is discrete. Okay, so this is another way of saying that we want a Fuchsian group in PSL2R, which is abstractly isomorphic with this fundamental group. Okay, so which is a free group. Okay, and you also want that. So remember, there was this vertex cycle condition. So we want that rho of B inverse. I think we had this element as a vertex cycle is parabolic. Okay, this is what we want. If you want to build a Fuchsian group, okay, so which gives you a once punctured torus as a quotient. This is what you need to kind of look at. You need to look at such a homomorphism. You need to find such a subgroup of PSL2R. This is just saying that you find a subgroup of PSL2R that is isomorphic with this fundamental group. Okay? And you want to look at this, so the space, the Teichmuller spaces will be all such homomorphisms. And you look at the quotient, I mean, so you look at the equivalence, so where, two representations, two such homomorphisms are the same, if and only if there exists some PSL2R element which conjugates that. Okay, so that one of gamma equal to A rho 2 A inverse for all gamma in pi 1 of S11. Okay, so this is what, so if these two homomorphisms, these two subgroups are conjugate, right? So then they're actually the same, gives you the same once punctured torus. Okay. All right. So how do you build such? Well, we already saw. So let me sort of generalize. Let me sort of see how many parameters how much freedom we had. Okay. So what we want is we want to get to. Yeah. So we can start. So we want a fundamental domain which is an ideal quadrilateral, right? And we want to pair sides, right? That's what. So once punctured torus we get by taking a ideal quadrilateral, and we have A and B, and so the pairing. So as a quotient, you want to get this, okay? And these lines, which are going sort of yeah. So these axes of these elements, they give you sort of curves, so geodesics. So you want to get to, you want to start with an ideal quadrilateral. So any ideal quadrilateral, as we just saw, you can convert to something like, looks like this, 0, 1, let's say x. Okay, so, or maybe I should say lambda, right? We were using lambda. Okay, so, and then we can pick elements which pair these sides. Okay, so this time I'm going to use A this way, and let's say B this way. Okay, so that this goes this here, and here this goes here. Let me write down some elements which does that. So we'll work in. I won't normalize to make it into PSL2R. I'll work in PGL2R. Okay, so if you look at, let's call it A hat. Which depends on x. Okay, so x. So maybe I should call it. So let me call it x. So it depends on x. This cross ratio, and this is the matrix XX 1x. Okay, and B hat again it depends on x, is 0x and 2. Is that correct? Or maybe, sorry, it's -1 and 2x. Okay? So these matrices actually do these identifications. So the claim, so let me label these also. So this is S1, this is S2, this is T1, this is T2. So the claim 1 is that for each x bigger than 1, A hat maps S1 to T1, and S2, and B hat maps S2 to T2. Okay? And this you can check. I mean, so what do you have to check? So A hat, so you have to check that A hat takes, so this matrix times, let's say 0, 1. Okay, so what's this matrix times 0, 1? So 0, 1 represents this point. Okay, because, yeah, so remember, so after the linear fractional transformations, you projectivize, right? So this really represents 0 by 1 on this line, which is RP1. Okay, so 0, 1, this goes to XX, right? Which is the point 1. So this is the point 0, this is point 1. So you can check that. So these transformations, once you normalize and make it into PSL2R, these takes this geodesic to this geodesic. Okay, so 0 goes to 1, and infinity goes to x, and so on. Okay? Any questions right now? So these are matrices that takes this to this and this to this. Okay? All right. Okay. So I didn't normalize. You have to maybe sort of so divide by something to make the determinant 1. But before that, so this is what happens. Okay. So any questions? Yeah. So where does infinity go under A hat, for instance? So A hat. So infinity is the point 1, 0. Okay, in RP1. So that goes to well, x1, which is, so this is infinity and that's x. So A hat will indeed take infinity to x, okay, and so on. Okay, so you can check for B hat also. Okay, so yeah, so now you have a quadrilateral and a side pairing. So all you need to check is that the vertex cycle is a parabolic element. Okay, so claim 2 is that if you look at the commutator of A hat and B hat, you do get a parabolic element. Okay, so I'm not going to do that calculation, leave that to you. So claim 2 is this commutator A hat, B hat. So I mean, yeah. So we can avoid the inverses if you want, but it's either way. Okay, so this fixes infinity and is parabolic. It's the vertex cycle for infinity. Okay, so infinity goes to 0, goes to 1, goes to x, goes to infinity, and the transformations are B hat, A hat, B hat inverse, and A hat inverse. Okay, so this you can kind of check. So that's the vertex cycle. Yes? Yeah, so it's this matrix, x, x, 1x. Yeah, so this defines an element in PGL2R, but as I said, PGL2R, you can normalize so that it's in PSL2R. Okay, and then it's an actual automorphism of H2, right? A hat is this transformation, right? And it should take, okay, maybe there are no hats here. Was that your concern? Yeah, so A hat takes this to that, and okay, maybe now it's clearer. Okay? So I've just written down a matrix that takes 0 infinity to 1x. Okay, this is a matrix which does that. And as I said, it's because of this, right? I mean, this is how you come up with with that matrix A hat. You know what the second row has to be, and you know what the first row has to be. Okay, so yeah, so I leave that to you. Okay, so so I'm kind of going back and forth between like PGL and PSL and the action by linear fractional transformations is actually a projectivization of the action of 2 by 2 matrices on R2, right? So I'm kind of going back and forth between various interpretations here. But you can check. If you don't like this matrix, you can come up with another matrix that you know lies in PSL2R and takes this geodesic to that. Just like we computed before, right? So you can kind of play around and do that. Now, so the Poincaré polygon theorem, so the claim 1 and 2 implies the Poincaré polygon theorem, which I wrote down earlier, that the gamma generated by A hat and B hat is a Fuchsian group. And in fact, it's a free group, right? As I mentioned, that there are no relations, there are no interior vertices in this polygon. So this gamma is actually one of these elements of the Teichmuller space of the once punctured torus. Okay? So and here we already see we have one parameter, this x. We could have chosen anything from bigger than 1. Okay, so we have one degree of one real parameter here, 1 degree of freedom. But there is more. So if you replace, so there's another parameter. So let me just do it here. So remember that when you identify sites, when you identify these sites, you are taking a hyperbolic isometry, so we're taking an automorphism of the hyperbolic plane that takes this geodesic to that. But these are infinite lines, so you could have also taken it here and translated. Okay, so there's an extra parameter associated with these identifications. Namely, you can translate first and then identify. Okay, so you can have that extra parameter. So let me just say, so if you replace A hat with A hat times M, and that's what I'm going to call A, where M is a hyperbolic, so now it's a hyperbolic element of PSL2R with axis S1. So remember that hyperbolic elements kind of acted by dilations. Right, and there was always an invariant axis, okay, between the two fixed points in the boundary, okay, which is some geodesic which it fixes, okay, so it translates along this geodesic. So if you replace A with this, so M is something which kind of translates up this geodesic, okay, so let me write down that M. So this M looks something like this. It's T0, 0, 1, okay, where T is bigger than 0. That's a hyperbolic element. Okay, right now it's in PGL too. Okay, so this doesn't have determinant 1, but you can always normalize. Okay, so it's a 2 by 2 matrix which is determinant positive. Yeah, I'll stop in 5 minutes. And so this gives you another identification. And if you replace, so let me write down what A is. A looks like TXX. And then Tx. Okay, so this is what the new A looks like. This is another identification of S1 with T1, and you replace B with. So let me erase this. So and you replace B with B hat n. So B hat with B hat n, which is my new B, where n fixes is translates along S2. So n looks something like this. It's S times x1 minus s, 0, 1, s bigger than 0. And B becomes, if you multiply these two matrices, you get 0x minus s, x1 plus s. So this is another identification of this geodesic with that. But you still need to check that the commutator is a parabolic element. Okay, so there's this extra condition. And so you have to ask yourself, when is, so A inverse, B inverse, AB parabolic? Okay, and so the answer is, so if you look at the computer trace of this element, now you know what the matrices are. Okay, so this is A is this, okay, and B is this. And if you try to compute the trace of this commutator, you should get S by T plus T by S. So when is it parabolic? It's parabolic when S equals T. So you remember that a parabolic, yeah, so maybe you need to, there's a sign here, but so it's either, so maybe let me take an absolute value. So I don't want to, so you could have chosen sort of the A inverses as well, but no matter what, so this, so there's this freedom that you had of choosing this translation before identifying. So these translations need to be both the same, sort of translating by the same amount if you want this commutator to be parabolic. Okay, so finally, so what happens is this extra parameter now, which is T or S, is the extra parameter that you have in this figure. If you want to build an ideal quadrilateral and you want to pair sides to get a once-punctured torus, you need two parameters. One is x, and the other is this T, okay, which is equal to S, okay, because you want this commutator to be parabolic. So finally, what you get is that the Teichmuller space, so you have the parameter space now, so the consequence is, if you want to apply the, so now you can apply, if S equals T, you can apply the point polygon theorem and conclude that you get a Fuchsian group. So the parameter space P, which is x comma t or x comma s, x is bigger than 1, t is bigger than 0, is the Teichmuller space. So there's a kind of a injective, it's a homeomorphism to the Teichmuller space. This is something you need to kind of prove. You need to show that this is indeed an injective map and so on. Okay, so but this parameter space actually describes all elements of which give you a once-punctured torus. So all the freedom you had in building a fundamental domain for your action, we've kind of used up. Okay, so all these, this was the polygon and this identification, and this actually this gives you a parametrization of Teichmuller space of the once-punctured torus. So the Teichmuller space of a once-punctured torus is homeomorphic to this set. This is actually something that's homeomorphic to R2. Okay, so some kind of domain. And if you want to think of the moduli space, so you want to now, so here, so remember we chose some generators of the fundamental group, right? So we had pi1 of S11, and we were identifying that with our gamma. Okay, so there was an isomorphism with the Fuchsian group, and isomorphism took the generators to A and then to B. So now if you don't want, this is what is called a marking. You're marking the generators of the Fuchsian group with generators of the surface. Okay? So if you don't want to mark, you get moduli space. So the moduli space, 1 is a quotient by Teichmuller space by some automorphisms of the fundamental group. So these are outer automorphisms. So how does this acts. Remember, Teichmüller space was looking at this homomorphism to PSL2R. Okay, so you could have changed the generating set of pi1 of the fundamental group. So if the changing of a generating set is an automorphism of the fundamental group, and certain automorphisms are given just by conjugating every element by a sort of fixed element, that's not going to change your representation. That's just going to conjugate your representation, which will be the same point in Teichmüller space. So you need to sort of quotient by something called the outer automorphisms group. So this is sort of, let me just say it's sort of, in the construction, in the previous construction, we had fixed the generators of S11, which is namely sort of A and B. Okay, so if you don't want to fix, so this was our marking. So this was like labeling the vertices in this ideal polygon case. So this was the marking. So so if you want to, and not to fix the generators, so if you don't want to fix these generators, this amounts to quotienting by automorphisms of the fundamental group, and these and you get, so you quotient so by the automorphisms, the outer automorphisms of the fundamental group, and this gives you moduli space, and you get the moduli space of once punctured tori. Okay, and you can see this. So we know a lot about what automorphisms of a free group look like, and so you can actually write down explicitly, if I had more time to have done that, what these automorphisms, how they take, xt, the pair goes to another x prime t prime, which you identify to get moduli space. So you can, so in this, this parameter space in xt coordinates looks something like this. It sort of is, let's say, x equals 1, and this is x, and this is t, right? So then, so x greater than 1 and t greater than 0. So it's some kind of domain like this, and you would have this outer automorphisms. This turns out to be GL2Z. Okay, so this GL2Z acts over here, and you get a fundamental domain, which is the moduli space of once punctured tori. Okay, so anyway, so this is the sort of the starting point, and this is like the so this is the group theoretic description or the algebraic description of Teichmüller space, what Teichmüller space is. You can also define Teichmüller space completely in terms of hyperbolic geometry. You build a hyperbolic surface. You build these quotients by gluing sort of basic building blocks. And last time, I was in ICTS last November, I gave a series of talks where I looked at Teichmüller space from that other point of view, okay, which is a more geometric point of view. This is the algebraic side where you can try to construct actual Fuchsian groups by looking at polygons, and then you look at how much freedom you have, and you can parameterize Teichmüller space that way. All right, so and you can do it not just for once punctured torus, for any genus and with any number of punctures. Right, so as long as the Euler characteristic is negative, it will have a hyperbolic metric. Okay, and so you can actually sort of look at Teichmüller space this way. Okay, so so I've run out of time. Sorry. So next time I'll do something completely different, completely independent of what I've been talking about. So in case you're completely lost, you're fine. Okay, so all right.